Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 21st, 2026, just 2 days ago. It introduces a framework that achieves a 3 to 4 times token compression rate compared to explicit chain of thought prompting, significantly accelerating inference. The paper is titled Render of Thought, Rendering Textual Chain of Thought as Images for Visual Latent Reasoning. And, as we'll see later, the implications for making latent reasoning both efficient and traceable are quite significant. To see exactly how they tackle this trade-off, Figure 1 compares the proposed method against standard approaches. First, in Panel A, we have the explicit chain of thought, which relies on generating a verbose sequence of text tokens, shown as purple squares, to connect the question to the answer. Next, Panel B shows previous implicit methods that compress this process into latent embeddings, the green squares, though this often creates an opaque black box. In contrast, Panel C introduces the Render of Thought framework. Here, the text is actually rendered into images to create structured vision embeddings, the blue squares, and these visual anchors then guide the latent reasoning process, keeping it both efficient and traceable. Alright, Figure 1 gave us the concept, and now Figure 2 breaks down the machinery. First, looking at the top panel, the rendering method converts textual reasoning steps, like a math derivation, into a single strip of image pixels. Then, in the bottom panel, the latent reasoning method uses this image as a supervision target. A frozen vision encoder creates blue visual embeddings from the image, while the large language model produces green latent tokens via a projection head. The system aligns these green tokens to the blue targets, teaching the model to think in visual representations before generating the final answer. So, Figure 2 introduced the components, and now Figure 3 details the two-stage training strategy. In the left panel, Stage 1 focuses on visual alignment. Here, the large language model backbone is frozen, indicated by the snowflake, while the visual projection head is trained to map internal states to the target vision embeddings. Then, moving to the right panel, Stage 2 shifts to latent supervised fine-tuning. Now the projection head is frozen, and the backbone is unlocked to learn autoregressive generation, enabling the model to produce these latent reasoning steps autonomously before the final answer. Okay, since Figure 3 explained the training, Table 1 now presents the main experimental results across 3 model architectures. The rows compare standard fine-tuning, explicit chain of thought, and the proposed render of thought method. Focusing on the middle section for the QN3VL4B model, we see a sharp contrast in the average token length column. While explicit chain of thought uses over 100 tokens, render of thought is strictly limited to 32. This drastic compression leads to the high efficiency scores highlighted in the final green column, even though the raw accuracy is somewhat lower than the uncompressed baseline. Well, Table 1 hinted at the efficiency gains, and now Figure 4 makes them concrete by tracking inference time in seconds per sample. On the left, looking at the GSM 8K August dataset, the tall bar for explicit chain of thought shows it dragging on for over 6 seconds. Meanwhile, the dark blue bar for the proposed method drops that significantly to 1.75 seconds. Shifting to the right panel for the GSM hard dataset, the difference is even more stark. The explicit approach climbs to nearly 9 seconds, while the render of thought method remains extremely fast at just 1.84. Alright, having established the speed, Figure 6 opens up the black box to inspect the internal state of the model during a complex task from the math dataset. The top section displays the input question and the rendered image strip used as the supervision target. Below that, Panel A plots the heat map of the generated latent embeddings, revealing a definite structure instead of random noise. In the center, the token similarity matrix in Panel B shows a solid red block of high consistency, indicating that the reasoning state stabilizes effectively as it progresses. Finally, the statistical plots in Panel C confirm this, as the values settle into a steady trajectory after the initial steps. Wrapping up, 2 takeaways stand out. Render of Thought successfully uses visual anchors to compress reasoning tokens by 3 to 4 times, drastically cutting inference costs. More importantly, it proves that latent reasoning doesn't have to be a black box, preserving traceability through visual alignment. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.